Hi everybody, so in this video we're going to continue with Differential Calculus 2 from Chapter 10, and it's the last topic of the chapter, 10.4, Optimization. So there are a lot of problems in science and mathematics involving finding the maximum or the minimum value of a function. The mathematics behind optimization, which is part of calculus, was developed actually in the 17th century, so it's not a new thing. But today it has many applications involving, for example, in business, things such as minimum cost, maximum profit. In the area of design, you have minimizing surface area or greatest volume. So what we're going to do is focus on these problems, which require the application of everything we've learned so far from differential calculus. So example 10.13 asks us to find the maximum area of a rectangle inscribed in an isosceles right-angled triangle whose hypotenuse is 20 centimeters long. So the first thing I need you to do is to pause the video here and make a drawing of the situation. Make a drawing of the rectangle inside that isosceles right-angled triangle and see what you get. This is the situation that is being described. So you have a rectangle inscribed inside an isosceles right-angled triangle. So we can see here the measurement of the hypotenuse, which is 20 centimeters, and this would be the right angle. Because it's isosceles, we know that this side and this side are equivalent. And also we know that this angle and this angle are both 45 degrees. This is 90 degrees. Therefore, we have another triangle here, which is also a right angle triangle that is isosceles. Okay, now why is this important? Because the area of this rectangle is going to be equal to x times y. But one of the things that is important when we want to solve these problems of optimization is that we do not want to have hopefully more than one variable. So we need to represent y in terms of x. So notice that they told us that the hypotenuse is 20 centimeters long. And if we take the base of the rectangle as x, that means that each one of these sides here, or these bases for this other triangle and this triangle here, are going to be 10 minus x over 2. So 10 minus x over 2 is the length of this side and the length of this side. But also, it is the length of this side. Therefore, the height or width of the rectangle. So we can say that this is equal to y. Therefore, we can put the area in terms of x. So the area of the rectangle would then be x times 10 minus x halves. And therefore, the area would equal 10x minus x squared over 2. So they want us to find the maximum possible area. So remember that these maximization problems are going to be solved using derivatives. So we would have to find the derivative for this area and then equal to 0 and find the maximum. So the derivative of the area is going to be 10 minus x. Therefore, the area will be maximum or minimum, we're not sure, right? When we solve for this equaling to 0. And obviously, x equals 10. So 10 is probably the value of x that gives us the maximum, I should say. Okay, so what about that? What do we do next? Well, the next thing you need to do is find the second derivative. of the area function that we found. And notice that it's simply going to equal -1. What that means is that this function has a negative concavity, or it is always concave downward. And because it is always concave downward, then 10 is definitely going to give us a maximum. Okay, so that we verify that this is actually a maximum, and we can now find the maximum area. So the maximum area is going to be, remember that we said that the area is equal to 10x minus x squared over 2. So then we would need to substitute x for the value 10 where the maximum occurs. So then the area, or the maximum area, I should put maximum here, is going to equal to 10 times 10 minus 10 squared over 2. And this is simply going to be 100 minus 50, which is equal to 50. But because we're talking about area and the unit is centimeters, we would say that the maximum area would be 50 centimeters squared. Very well. So in the next slide, you're going to see a general strategy for solving optimization problems in steps. So step 1 is to draw a diagram that accurately illustrates the problem. You have to label all the known parts of the diagram using variables. Label the important unknown quantity or quantities. For example, x for base and y for height in the previous example, 10.13. Step 2, for the quantity to be optimized, such as the area in example 10.13, express this quantity as a function in terms of a single variable. From the diagram and or information provided, determine the domain of this function. So one of the mistakes I made in the previous example was that I did not write the area as a function. So it should have been a of x, not just a. So keep that in mind when you do these problems. Step 3 says we need to find the derivative of the function from step 2 and determine whether the derivative is equal to 0. This value or values of the derivative, along with any domain endpoints, are the critical values to be tested. And they say that in example 10.13, we should have tested x equals 0, x equals 10, and x equals 20. Now, I don't think this makes any sense because we're not going to have a base length of 0, nor would we have a base length of 20 because this was the size of the hypotenuse. So obviously there could not have been a rectangle inscribed inside that triangle. So in this case, this doesn't make any sense. Okay, so let's look at step 4. And for step 4, they say that using algebraic or graphical methods, algebraic would be the second derivative test, which is what we did, or graphical using the GDC, analyze the nature, whether it's a maximum, minimum, or neither. Then it says, make sure you answer the precise question that was asked in the problem. Well, that's a good thing that they say that because in their example, the problem was asking for the maximum area. And if you look at the book, they forgot to find the maximum area. They only found the maximum value of x that gives you the maximum area. So they're not doing what they're preaching, but you guys know better and make sure that you answer the actual question. Very well, so next we are on example 10.14, and it says 2 vertical posts with heights of 7 meters and 13 meters are secured by a rope going from the top of one post to a point on the ground that is between the posts and then to the top of the other post. See diagram. The distance between the 2 posts is 25 meters. Where should the point at which the rope touches the ground be located so that the least amount of rope is used? Okay, so the first step, remember, is to make a diagram. In this case, they say see the diagram, which means that it's already done for you. But as a practice, pause the tape here, or the recording, I should say, pause it here, and make the drawing, and then you will compare with the actual drawing. So here it is. This is what you should have drawn, or something very similar. Now, we see all the information, and we have two posts that are separated by a distance of 25 meters. We have one post with a height of 7 meters, another post with a height of 13 meters. Okay, so how do we relate this information? Notice that if we designate this distance here from Q to R is going to be that point on the ground that is between the posts. Uh, so from Q to R, we can call that distance X. Therefore, for the other triangle that is formed here, we would have a base of 25 minus X. So what is it that they want us to minimize? They want us to minimize the length. Now remember that we have to say that this is a function in terms of X, which is something I forgot in the previous problem, like I said. So they want us to find the minimum length for the rope that is the distance A plus B, as we can see here. So this would be the rope, so we have to have A plus B. Now we have to put A and B in terms of X, but because these are right triangles, as you can see here, we can use Pythagoras, because then A is simply going to be equal to the square root of x squared plus 7 squared, which is 49. Then for B, we would have that it is equal to the square root of the base 25 minus x squared plus the height squared, which would be 13 squared, or 169. Now we should expand this, and this is going to give us that B is equal to, and we always want to put x squared first, so x squared minus 2 times 25, so that'd be 50x plus 25 squared, which is 625, and this plus 169. Then finally, we have that this is going to equal square root of x squared minus 50x plus 794. Therefore, we have the function that we need. So that would be that L of x is equal to a plus b. So distance a in terms of x is x squared plus 49. And then distance b in terms of x would be square root of x squared minus 50x plus 794. Okay, so we have accomplished the second step almost. Oh, we need a domain. So the domain, notice that it has to do with this distance, 25. So we might have that x is 0, but not 0, because that wouldn't make any sense. It has to be greater than 0. X has to be greater than 0, but less than 25. So this would be the relevant domain for this function. The next thing we have to do is find the derivative of this, because they want us to find a minimum. And obviously we can do that by equaling the derivative to 0. So the derivative of L in terms of x. Now remember that we can rewrite square roots using exponents. We can use the exponent 1/2. So let's erase the square roots and substitute that with parenthesis and exponent 1/2. Okay, and now it's easier to find the derivative. Remember that here we have to use the chain rule for each one of these. So this would be 1/2 times x squared plus 49 to the negative 1/2 times the derivative of the inside, which is going to be 2x plus 1/2 again, times x squared minus 50x plus 794 to the power of negative 1/2 times the derivative of the inside, which would be 2x minus 50. Okay, but this can be simplified. We can simplify this because notice that I can cancel out this 2 with this 2. Also here, I can factor out 2 and make it 2 times x and 2 times negative 25. And then this I can cancel out with this. And therefore, I can write the derivative for L as being equal to x over square root of x squared plus 49. Because this exponent is negative, I can bring this down and make it a positive exponent. And this plus x minus 25 over the square root of x squared minus 50x plus 794. So we have to equal this to 0 and solve for x. That's what we're going to do next. So this is what we have to solve, right? Equaling the derivative to 0. So notice that we have two fractions. Before we can actually solve this, we need to add the fractions. So how do we add these fractions? We would have to multiply this times this, and then cross multiply here, right? X times this, the square root down here, and this times that. So we cross multiply, and we multiply the denominators as well. And notice that this is going to give us x times, and we write square root of x squared minus 50x plus 794 plus square root of x squared plus 49 times x minus 25. And on the bottom, we are going to get square root of x squared plus 49 times the square root of x squared minus 50x plus 794. So this has to equal 0. Now the good thing about this having to equal 0 is that we can forget about this part, the denominator, because the denominator will never equal 0, and it's irrelevant when we want to find which value will make this equal to 0. So how do we solve such a big equation like this one? What we can do is send this part to the other side. So if we do that, we're going to get x times square root of x squared minus 50x plus 794 is equal to negative, and I'm going to rearrange this a little bit, x minus 25 times the square root of x squared plus 49. Okay, but now notice that we have a negative in front of this parenthesis. We can get rid of this negative by switching the signs of these values inside the parenthesis. So we could rewrite this as positive 25 minus x. So we're going to do that. So 25 minus x times the square root of x squared plus 49. So next we would have to square both sides. So let's square both sides. And we're going to get x squared times x squared minus 50x plus 794 is equal to 25 minus x squared times x squared plus 49. So here we have to keep expanding and then solving for x. So we're going to get x to the 4 minus 50x to the 3 plus 794 x squared is equal to, we have to expand this, which would be x squared minus 50x plus 625. And then we would still have to multiply this by x squared plus 49. So we have to do a little more erasing, and we will continue on the top. So this is the point at which we had arrived, and we're going to continue to expand. So we're going to get x to the 4 minus 50x cubed plus 794 x squared is equal to the expansion of this expression, which is going to be x to the 4 minus 50x cubed plus 674x squared minus 2450x plus 30,000 625. Okay, then we want to bring everything to the left-hand side and equal to 0, and then figure out a way to factor all this. Okay, so if we do that, notice that we can cancel out x to the 4, x to the 4, and minus 50x cubed, 50x cubed. So this simplifies the problem a lot more. So this is going to give us 120x squared plus 2,450x minus the 30,625. So we have to equal this to 0 and solve for x. So this is easier because now we have a quadratic equation. Here we could factor out 5 and then use inspection to factor the 3 terms that would be remaining. And we would get 5 times 4x minus 35 times 6x plus 175. And this equals 0. So we can see that the solutions are here, 35 fourths, and then for this other one, we would have 175 negative over 6. Okay, so this solution doesn't work because it's negative. And recall that we said the domain was between 0 and 25. So x is greater than 0 but less than 25. No negatives since we're talking about distances anyway. So it looks like we have a solution. We should still test this with regard to the endpoints 0 and 25, just to make sure. So for 0, you have to plug it into the original function L. And if you recall, L of x is equal to the square root of x squared plus 49 plus the square root of x squared minus 50x plus 794. So if we plug in 0, we're going to get L of 0 is going to be square root of 49 plus the square root of 794. And this is going to give us approximately 35.18. Let's test for the value we found. So if we plug in 35 fourths, you can test this for yourselves. If we plug that in, we should get about 32.02. And then if we test with the endpoint 25, that would give us approximately 38.96. So at least in this interval, it looks like this is a minimum value. But next we are going to verify this solution using the graphing display calculator. Very well, so notice that we have L of x plugged into the graphing calculator. But before I actually hit the graph button, we want to take into consideration the domain and range of the function in order to display it appropriately. So we go to the window, and normally by default, the factory settings have the windows at -10 and 10 for x minimum and x maximum, and the same for y minimum and y maximum. I'm going to leave the x minimum at -10, but I'm going to change the x maximum to a value, say, such as 30, which is over 25, which is the upper bound of the domain. We're going to leave the y minimum at -10, but for the maximum, I'm going to use 50 because if you recall, we had values for the domain that were above 30. So with this information, we're going to hit the graph button and we're going to display the graph. So there's the graph. And now we're going to find the minimum using the second function key. And then we hit trace button for the function calc. And under calculate, we will choose option number 3. Next, it says left bound. So I'm going to move the cursor to a point on the graph to the left of what I think is the minimum. So once I reach a considerable height above that minimum, I'm going to hit enter, and that would be the left bound. Now it asks for the right bound, so I'm going to move to a point on the right-hand side of the graph, which is above the minimum. So somewhere around here would be enough. Now let's hit enter, and we have the bounds. Now we can guess, and notice that we get 8.75 for x, that would be the minimum, and 32.0156. Let's recall that the answer that we had before for x as a minimum was 35/4, which is precisely 8.75. So there is the minimum, as we can see in the graph. All right, but we have to give an appropriate answer to the question. And in the question, they wanted to know at which distance, right, or which distance from between those two posts that we had should the rope touch the ground. So let's make a quick sketch of this situation. Remember that we had 2 posts, and we had a distance x and another distance which we deemed 25 minus x. So that point has to be at a distance x from the smaller post. So we can say 8.75 meters from the base of the shorter post, which was 7 meters, and the larger post, remember, was 13 meters. Okay, but also we had to answer about the length. So we could say then that the minimum rope length would be approximately 32.02 meters, which we got from the solution. Very well, so here we are in example 10.15, and it says 4 meters of wire is to be used to form a square and a circle. How much of the wire should be used to make the square, and how much should be used to make the circle in order to enclose the greatest amount of total area? So they want us to maximize the total area. The first thing you need to do in these problems, as usual, is make a sketch. So pause the video at this point and make a sketch, and then you will make a comparison to what the actual sketch should be. And there it is. That's the sketch, or something similar to this is what you should have done. So we have a square with sides length x, and we have a circle with radius r. For the time being, we don't have a radius in terms of x. And that's something that we're going to need to be able to create a function in terms of x only. So how can we relate these two? We can relate them with the length of the wire, because we know that the perimeter of the square is equal to 4x, and we also know that a perimeter of a circle is its circumference, which is 2 pi r, and this sum should equal 4. So from here, we can rearrange and write this equation for r in terms of x. So notice that we can get 2 pi r is equal to 4 minus 4x, and then r is equal to 4 minus 4x over 2 pi. We can factor out the 4, and this would equal 4 times 1 minus x over 2 pi. Then we could cancel out the 2 and get a 2 here when we divide 4 by 2. So we get that the radius in terms of x is equal to 2 times 1 minus x over pi. Okay, so because we want to maximize the area, we know that these areas summed would be equal to x squared plus pi r squared. But we already said that we need to have this in terms of x only. So a function for the area in terms of x only would be x squared plus pi times r in terms of x, which is this. So it would be 2 times 1 minus x over pi squared. So we're going to have to expand and simplify this, and then we will find the derivative as usual, right? So let's say then that a of x equals x squared plus pi times 4 times 1 minus x squared over pi squared. And because this is multiplying, we can get rid of pi here and then leave 1 pi only there. Okay, so area in terms of x will be x squared plus 4 times 1 minus x squared, and this over pi. So let's make it a fraction, 4 over pi times this. All right, so let's do the derivative. Let's do the derivative, and then we will equal the derivative to 0, right? So the derivative of the area will be 2x plus, and then here we have to do the chain rule, right? So this is going to be 2 times 4, 8 over pi times 1 minus x, and to the power of 1, because 2 minus 1 is 1, times the derivative of the inside, which would be negative 1. Okay, so finally this is going to equal 2x minus 8 over pi times 1 minus x. For now, we're going to leave it like this, and we need to solve the equation for this derivative equal to 0. So we're going to erase and we're going to work on that. Very well. So recall that we have that the derivative of the area is equal to 2 times x minus 8 over pi times 1 minus x. So we have to equal this to 0 and solve for x. Luckily, this is linear, so it's not going to be so hard to solve. Now we have two separate fractions, and notice that this fraction here is over pi. So in order to solve these fractional problems, we need to have the same denominator. So notice that we can rewrite this as 2 pi x over pi. So 2 pi x over pi. And once we have this situation, we don't have to worry about the denominator and just solve for the numerator. So we have that 2 pi x minus 8 times 1 minus x is equal to 0. So let's distribute, and we're going to get 2 pi x minus 8 plus 8x is equal to 0. And we're going to solve for x, so we can rewrite this as 2 pi x plus 8x is equal to 8. We can factor out 2 and x, so we can say that 2 times x times pi plus 4 is equal to 8. And then since we want to solve for x, x would be equal to 8 over 2 times pi plus 4. We can simplify this, and then we get that x is equal to 4 over pi plus 4. Now, if we plug that into the calculator, we are going to see that this is approximately equal to 0.5601. So once we have found this value, 0.5601, which supposedly maximizes the enclosure to the greatest amount of area, we also have to test the endpoints of the domain. So the domain here for x is that x is greater than or equal to 0, but less than or equal to 1. Well, why so? Because x is the length of the edges of the square. So when x is 0, all the wire goes to the circle, and when x is 1, all the wire goes to the square, right? Because we have a total length of 4, and if the lengths of each edge are 1, then the perimeter of the square would be 4, therefore it would require all the wire. So we have to test these values inside the original equation that we found for the area, and we said that the area of x is equal to, remember, x squared plus 4 over pi times 1 minus x squared. So then if we plug in 0 for x here in the area formula, we are going to get exactly 1.273. If we plug in the 0.5601, that's actually going to give us the same amount, 0.5601. If we plug in 1, we're going to get 1 for the area. So notice that we will get the maximum area when x equals 0. Why is that? Well, because the maximum area will be enclosed if we use all the wire on the circle.